Hi, in this video I'm going to review Einstar 2 laser scanner from Shining 3D. This review sample sent to me by a viewer from this channel is a loaner, so I will return it to him after this review. Comes with the glass calibration board, so it's calibrated to the reflective marker. So this is a true laser scanner. The calibration board is the smallest that I have ever seen. Maybe they want to put this inside the carrying case, so they want to make it a bit more compact, and the scanner is quite small, so they don't want to put a larger calibration board into that case. Let's see how the accuracy would be. So in the front we have a pair of a stereo camera. I think it's 2 megapixels. The lens is large, it's a wide angle lens, so they can put the lens spacing narrower. It has a RGB camera, infrared projector here, 2 of them, and one laser projector for the parallel lines. It has 17 parallel lines. In the back it has a start stop button and also a plus minus sign for exposure adjustments. Come with 2 batteries. They have a spare batteries with a charger. It's 3.6 volt, 5500 milliamp hour. It has an integrated Wi-Fi, and also you can plug it to your computer directly using the USB-C cable. So I'm going to show you both in this video. I've tried different distance. I found that the maximum marker spacing is 15 centimeters, and you have to lean the scanner about 60 degrees from the scanning surface. If you put it like this, the scanner won't be able to detect the markers. You need to lean it about 60 degrees, and it can capture the marker spacing of 15 centimeters. See here, it's 15. It's kind of extreme, but I recommend that if you place it like 10 to 12 centimeters, this will be more effective. Now it's losing a track, see here. So I put it in a repeat pattern. It cannot detect the difference of the dot that I place because I have 9 markers here. Now in the monitor it's more than 9. So you have to place it randomly. Let me try again. You need to do it a bit random. With the Crevasse scanner, it doesn't have to be random. You can place it like in the pattern the scanner will detect. Okay, now it's 15, somewhere around 15 will be maximum. So if I put it random, now it can track correctly. So working distance 26 centimeters. Speed test. "41 seconds." If you look at the scan result here, it produced 3 million points. The pad size is 570 times 420 millimeters. So it has 239k square millimeter. If I divide this by 0.09, because the resolution is 0.3 square is 0.09, so it should produce 2.66 million points, which is the true resolution of this pad. This scan give 3 million points. This speed test is valid. The scanner give the true resolution. Okay, so I'm going to scan the side first. Speed is good, it's very fast. Extremely fast for 0.25 millimeter resolution. You can scan this helmet in just less than 30 seconds. The black color is a bit difficult to see. It has a very low leaning angle. You can lean it almost parallel to the turntable. The leaning angle is good. Contrast color is good. It can capture black foam inside the helmet. They have a plain clipping function. Let's try it with the markers 1, 2, and 3. Create plane. Apply. Select this. They have a compatibility with the space mouse. The orbit center cannot be set using the space mouse, so I'm not going to use it. So I'm going to use the mouse. With the mouse, it's better. You can set the orbit center, but with the space mouse it's difficult to control. I skip the space mouse, and then I'm going to fuse the point cloud. They have two options. This one with the optimize, this one is the generate point cloud. I'm going to use the generate point cloud. Okay, so here's the point cloud. It has some striking lines. Yep, striking line. Let's do the mesh to see if the striking line will be disappear. The maximum 20 million triangles. Let's see how much the mesh it can produce. The striking line that you see here is caused by the scanning surface that is too far from the marker. So if you don't want to see this striking line for the Einstar, you have to apply the marker directly onto the helmet. So the depth between the scanning surface to the marker for the Einstar 2 is shallower than the one from Clarity. Here's one from Clarity. It gives a much smoother surface when scanning on the same turntable. Okay, let's try to see how well it can track a thin shell on both sides. I'm going to scan this and flip it over to the other side. This scanner has a very large FOV. I think it can flip to the other side. I get 84 frames per second. Ignore my hand, I just need to test tracking only. Okay, let's scan this. Okay, it's quite fast. I mean, it's turned to blue color. Let me turn this. Okay, now I can flip. Okay, so I can flip to another side. You need to find the angle. Now you can scan both sides in one go without doing the global marker scanning. It has global marker scanning mode. Okay, so the result, this one is better than the helmet. On both sides, quite smooth. Good result, and it removes all the marker, see here, without any marking. So marker removal also works pretty well. Because the eggshell is not perfectly round, it's about 50 microns out of roundness. So if the scanner can detect this 50 micron difference, it would be able to align these three scans together automatically. Okay, so we have project 1, 2, 3, all trim up. Right, 1, 2, 3. Let's align them together. You can only align one pair at a time. It cannot do alignment with more than 2 scans. And I'm going to align the first one to the third one. Going to use automatic alignment. Apply. Okay, so it can align the first scan. Next, okay, this will be the group 1. Float window will be the second scan. The alignment is wrong. You see that pink one? The pink one, it has to go here. The software align this eggshell upside down, so it cannot detect the difference of the eggshell variation in the range of 50 microns. 150.04. I have already calibrated the scanner before I perform this test. I have a measurement tools. Okay, that's point number 1. That's point number 2. Okay, it's read the software read 149.961. So the other is 79 micron. If measure within the software, let's try this in the cloud compare. Maybe the software is inaccurate. Okay, so it's read the same 149.95. If you ask me, I'm going to trust cloud compare more than any other software. It's very accurate. The point picking on cloud compare has some computation to translate your mouse cursor onto the point cloud. I think I better do it like this. Yeah. We have a very wide, good tracking performance. It's not losing track at all. Very good. Okay. It has to be on the extreme edge. Let me try again. Okay, 1999.68. About 120 micron of the drifting error, or about 60 micron per meter. Okay, next the resolution test. I'm going to make a 3D scanner VR. It has fine texture, and I'm going to compare it with the other 3D scanner. I'm going to use the highest resolution, 0.1 millimeter. Okay, this is a warning. If you're scanning with high resolution, like this one, sometimes it's going to give you a pop-up message. To be able to move to the second scan, I need to fuse the point cloud first. I'm going to flip this over to scan the bottom side. New project. What? Scanner mismatch. What do you mean mismatch? Mismatch. It still connect. It's the same scanner, right? It's the same scanner. I want to make a second scan. I have to do this. Create a new project. It's not support. Okay, let me try this. I'm going to make a new project. R2. I try to import the scan from the first scan. It should work. 0.1 millimeter. Okay, next I'm going to bring in the scan from the previous scan. Only project create with the same scanner. I create with the same scanner. I didn't change the scanner. It has to be some kind of bugs when scanning with the high resolution. So I cannot merge this out. But I did that with the 8 0.2mm. It has issue when I scan with a higher resolution. So I have to, no choice, I need to just use the single scan for the comparison. Because the head area is all captured. Okay, let's take a look at the result starting from the most right. We have Vega and Autolight. Autolight is a bit mushy. Auto is better, 0.15mm resolution. MAF-T is still the best scan in this test. Raptor with the 0.1 is very close to a MAF-3. S1, X1, a comparable result if you look from the front. High contrast, like on the eyes, is not captured. Okay, there's some noise around the eyes. Okay, it's not here. A bit of the noise here and there, not much. It's no noise. No noise. This one is what? Matrix. Matrix is very mushy. Okay, let's try the back side. I can see that it's softer. At the same resolution, 0.1mm is softer than 0.1mm from Crevasse scanner. So the resolution is a little bit less than the scan from the Crevasse. On the left, Einstar 2. On the right, Raptor Pro, scan with 0.15, same resolution. If you look at the headshot, they look quite similar because this model, it doesn't have much of detail. The Einstar has some striking lines on the face here. Details on the flowers look quite similar. Yeah, on the left and on the right, very close. I call it no different, I think. But if you scan this with 0.3, you will see different. 0.3mm will give a much lower resolution. Okay, next let's test a black color object with some deep pocket. It's the same object that I used for testing the 3D scanner. Let's see how much the Einstar 2 can capture this. I made two scans, front and back side. We choose 0.15mm, same as the other scanner that I test. I can't type 0.155. I can't type number 5. Next, I'm gonna scan on the other side. Top side has a lot of pocket. New scan. Scanner mismatch. Maybe I need to connect it to the cable. Now let's try connecting this to the cable. Okay, now it's connected. This is a new project. Let's start over again. Project list, add. Okay. So if you use the cable, you can do multiple scans in one project. I can't see because the noise is blocking. Okay, so we have to scan now. I'm going to do the project alignment, fixed window, float window, automatic alignment, apply. Okay, so we have an issue here. It cannot do automatic alignment, same as when I align the eggs. Let's try it one more time. No, it's because of the precision is too low. Manual alignment, 1, 1, 2, and 3. Usually it doesn't have to be precise. It defines the curve and taper, and then it will align it together. So you need to do manual alignment to get this done. Other scanner that I have tests, it can align automatically. You're gonna see some seam line. Because the first and the second scan has different dimension. Now it's reading 20.16. The alignment. Next I'm gonna crop this, trim it to the thin section. 20.183. Okay, let's compare it. On the right is the X1 Raptor, S1. They give a very similar result. Okay, so if you look deep into the detail, there's some noise, look like a noise in the indentation of the letter. They are both scanned at the same resolution, 0.15 millimeter. Okay, so the X1 give a cleaner. I think it's sharper too for the text. There are some noise in the pocket. Okay, let's move to the back side. Okay, because it doesn't have a single line laser mode, so it cannot capture deep into the pocket. Looks like the Raptor can see it through the bottom of the pocket better than the Einstar 2. See, it's capture more area. This one is a little bit less. See the side hole here is all captured. For the Einstar, some parts missing, because I think it's because it uses a very wide angle lens. The X1 and the S1, it has single line laser. The Raptor can capture more on the fin array area. If you want to reverse this, we have to do some manual measurement in some area because it's not capturing deep pocket very well. Okay, and if you look at the top here, it's a seam line between the two scans. Okay, the final test, I'm going to scan this metallic. It's not that glossy, has some texture detail. Yeah, I can compare it with the Raptor Pro. I'm going to use the same resolution, 0.2. I use cable connection this time. The next scan will be this side. Okay, you see, if I don't use wireless, I can add a second scan without any issue. Five markers. Okay, so here's the final comparison. On the right is the Raptor Pro. On the left is the Einstar 2. They are both scanning with the 0.2 millimeter resolution. Look from this distance, you can see the Raptor Pro can give a higher resolution than the Einstar 2. Let me move it closer. You can see it clear. The working distance for the Einstar 2 is further from the scanning surface than the Raptor Pro in a 7-line mode. So the Raptor Pro can get closer to the scanning surface. So with the same resolution, it will give a finer detail than the Einstar 2. The difference is not much with the 0.2. With the higher resolution like 0.15 or 0.1, the difference will be wider. But this part is not small. In a regular use, I will scan this part with 0.2 millimeter resolution. And for the flat part, they look the same. Resolution is the same. What different is the scanning speed and the accuracy in which the Einstar 2 finished the scanning job much faster than the Raptor Pro, and the Raptor Pro will give a much higher accuracy and precision than the Einstar 2. So that's a tough decision to make. Raptor Pro is way more expensive than the Einstar 2. On the back has no detail to distinguish the two scans, so you won't see different here in the back side. Einstar 2 costs $999 on their website, and the cheapest cross-line laser from Creality, Raptor Pro, costs $1,899, which is almost twice the price of the Einstar 2. And Einstar 2 also comes with a wireless functionality that you can connect to your PC. We are using the cable, and for the Raptor and Simoon series from Creality, you need to purchase the scan bridge separately, and the Wi-Fi connection from the Einstar 2 is very fast, almost as fast as the Simoon P1. But there's some issue in the software that you cannot do multiple scan when connecting to the Wi-Fi. Okay, so when you compare the speed, the Einstar 2 has become the fastest laser scanner I have ever tested. It finished that cutting mat scan with a 0.3mm resolution in 42 seconds. And it's even faster than the Simoon X1 in the cross-line mode. Okay, and for the marker spacing, it's 15 cm for the Einstar 2, wider than the Raptor Pro. Raptor Pro is 10 cm, so it requires less marker. But when you scan with the Einstar 2, you need to make some angle to the scanning face. You can't just point it perpendicular to the surface, it won't track. You need to lean about 60 degrees, I think, from vertical, and it will give you a good tracking performance. Okay, next, the working distance for the Einstar 2 is 26 centimeters, so it's shorter than the Raptor Pro, because when the camera is back off from the scanning object, it can see more of the markers. Okay, and for the precision test, that when it's failed, unfortunately, the Einstar 2, it cannot detect the variation on the eggshell, which is around 50 microns, and when I try to merge it, it cannot merge the eggshell automatically. And also, when I scan the bumper, it also cannot align automatically, while the 3 scanner from Creality here, when I test with the bumper, it also can align the bumper with just 2 scan automatically, because it the overlap area has the same geometry, so the software can align them automatically. But for the Einstar 2, it failed. And when the precision is low, it will reflect in the accuracy as well. The accuracy alert from Einstar 2 is above 50 micron. It's too high for reverse engineering use. I would keep it under 50 micron, because when you trace the line using CAD software, you're gonna add more error into that. And if you are using for a 3D printer, the 3D printer has 0.1 millimeter of the accuracy error, and you add up that 85 micron into the part would not fit. So you may need to use a vernier caliper or other measuring tools to verify the accuracy before you actually reverse it in CAD.